is about knots in relation to physics, and knots in relation to ideas, and it's mostly geometrical with some movies, and so I hope it's a good, I hope, good talk for this time of day. And there's a lot of interesting material in this, probably more than we can cover in an hour, so you may find me skipping portions, or you may be applying the book at some point. So let's see, what do I have here? I'm beginning with a story. Oh, does someone have a laser pointer?
Is there a way to enlarge?
Larger?
Larger picture.
Larger.
Has anybody got any?
Sit closer.
Focus.
No.
You have to go farther back. You have to take the projector back.
No.
We could put the projector back here a little ways, or the whole table back.
Okay.
How's that? And then
I'll just let you focus.
want to focus it again. Is that good?
Yeah, thank you.
Okay. I was asking, does anybody happen to have a laser pointer?
I've got this one that the AAA batteries are in on their last leg. That's what seems to be the problem. Nobody's got any.
No, doesn't matter.
I mean, I could go get some. I'll just go get some. I think that's a good idea.
Okay, so I begin my story back in the 19th century with Sir William Thomson, who had a wonderful theory of what atoms should be, and his theory was that atoms were vortices, knotted vortices, in the luminiferous ether. A tremendous theory and a really beautiful idea, as long as you had a theory of the background to all of space being some kind of fluid in which there could be vortices. So this went on for some time until the notion of the ether started to change into abstract spaces. The idea of knots in space has not changed, but Kelvin's theory kind of disappeared. But it began mathematical studies of knots in fluids, and knots in fluids continues to be vortices and so on, continues to be something that people study. What we're looking at here is a vortex in water produced by dolphins who make them by blowing water quickly through their blowholes. And then they play with them, according to YouTube videos that I have seen and you may have seen. So that's not a knotted vortex. But Kelvin had the idea of a knotted vortex. And this is like strings, but not in higher dimensions. That dimension 3, the dimension of the luminiferous ether. And that was his idea. And it was very popular in general. For example, the same idea infected people who were thinking meditatively. And you saw this in Richard's slides. This is the Leadbetter-Besant atom, inspired by Kelvin's vortex theory of atoms. But they had the idea that this was the beginning of the transition from the spiritual to the physical in the form of this kind of some kind of process. And this is the way they depicted it and claimed to see it. And they, in fact, wrote books about meditative chemistry. I don't remember what their term is, where they had all sorts of interactions that they were cataloging. They were preceded by Babbitt, and I think they might have got their image from Babbitt. Babbitt had a book on light and color, something like that, in which he had this kind of more complicated vortex atom. But we're talking about vortices. And then here's an attempt to depict something that might look like that. This is simply a curve written in three-dimensional space with cosines and sines and some related frequencies. But you see, you can have some knots that are made from simple equations that look something like the vortices that they were thinking of.
Can I interrupt you? My mathematics can...
I'm sorry?
Can I interrupt you? My mathematics can generate exactly that. That special algebra generates exactly those figures.
The algebra that you use
that I
lets you generate figures like
lets
that.
me generate these figures. I actually drew these.
I'm not surprised. Because your algebra, of course, contains lots of trigonometric functions, but it'd be interesting to see what you generate.
No,
Perhaps you have them on your computer.
no, unfortunately, it's on the wrong computer. But anyway, there was just
Yeah. Of course, it's a wonderful game to make pictures of knots using a computer. It's not hard at all with Mathematica or Maple or one of these programs. You just try writing some things and see what you get. Or you can be more systematic about it. For example, his name slipped my mind, but there's a student from some years ago who did a PhD thesis under John Simon, and he would take knots that had been generated by some other process, so you had a set of points, consecutive points in space that would form a knot if you connected them all up, generated by some other computer process. But then you can try to fit it with a finite Fourier series, and then you get formulas like that involving trigonometric functions that will draw these things beautifully and smoothly, and then you can play with them that way. It's a nice game, and computers let you think of knots in terms of equations in a way that you couldn't do if you were just thinking by hand. Now, then there's symbolism. For example, the vortex or snake that eats its tail is a well-known mythological symbol, and it was the symbol of the American Society for Cybernetics for a long time, a symbol like that, inspired to them by Heinz von Forster, I think. But then more recently, and it isn't actually due to me, you might think so, they took a knot for their logo, this knot. I could say something about that now, but I think we don't have time. Here's the truffle knot, rendered as three-dimensionally as you could, right? And then on the other hand, here's a very crude diagram of the trefoil knot. But I wanted to say some things about structure. And one of the things that these diagrams have is that you can think of them as generating a category. You see, it's got three arrows. Each arrow points to one of the other arrows from one of the other arrows. You start from the arrow A, and you have an arrow which goes along and bumps into the arrow B. So you can think of that arrow as a morphism in category which has as its domain A and its codomain B. It's a morphism from A to B. Every morphism that is implicit in this diagram is a morphism between morphisms. A category is said to be a higher category if it has that kind of structure, that there are categorical arrows that are actually objects, and the arrows between arrows are morphisms of a higher type which go between them. And in this case, there aren't any objects of any other type, you see. The only objects in this category are A, B, and C. There are lots of morphisms other than the ones that are depicted because we're going to generate a category from this diagram. That is, in a category, you have to be able to compose arrows. So you could start in A and take the arrow. You can use the diagram below if you want to keep track a little more easily. Now you have a category with three objects named A, B, and C, and generating arrows C, A, and B that happen to be labeled the same. If you wanted a composite arrow, you could go from A to C by doing C and then doing A, you see. And if you have, this is just a remark about categories too, if you want to generate a lot of categories from situations that occur, you may have a situation where there's some basic arrows. They could be arrows in a knot diagram, or they could be pathways from city to city in a map or anything like that. And then you want to be able to compose your arrows, and that gives you lots more pathways. So if you have a map and you're looking at it, or the subway system, and you think of all the pathways that can be drawn that go from one place to another, then you have all the arrows in the category. The only ones that you don't have are the identity arrows, because you didn't mention them, that you can go from a place to a place and it doesn't do anything. So So you see that a knot diagram connotes a higher category. And then the kind of things that you do to knot diagrams are things that you can think of as having been done to a higher category. And on the other hand, if you had a higher category of infinite height, so that the only objects were morphisms, why then you can imagine drawing a diagram like this. It might be huge, or it might have a small generating diagram like this category does, but that would be, you would have a category of infinite height, just meaning there aren't any base objects, there are only morphisms. You would draw a big diagram for it, and it would look something like a knot diagram, but maybe not exactly. For example, in the knot diagram, an arrow comes in, and then another arrow immediately comes out, right? And in a more general situation, an arrow comes in, and maybe a whole bunch of arrows come out, and they aren't correlated this way. So there's some special extra correlation that's going on for these that make them knot diagrams. But it's clear that you could think of the theory of categories of infinite height as a sort of species of generalized knot theory. And that's a project of mine, which is sort of percolating. Now, on the other hand, here is a point of view on knot theory which you can now think of as applied higher categories. I color each of the morphisms with a color. These colors are, let's say, red, blue, and green, all right? Or maybe I should call them solid, brick, and crosshatched, and then every time I look, I'll say the right thing. And then my rules are, at a crossing, I have to color either with 3 colors or with only 1 color. And then I'm allowed to change the knot diagram by moving it around according to topological ideas. So I can change it like that and move it, but then I can push it underneath itself. And you see that when I pushed it underneath itself, I was able to continue the coloring. From the point of view of categories, I acquired a new morphism, and that new morphism had to be labeled, colored in that way in order to continue the rules, right? And then you see, you keep pushing it around, and every time you push it around, you can uniquely relabel it. And it gets more and more complicated and more colored as you go along, but only with 3 colors. But what you can then convince yourself, if you think about this for a little while, is that you will always have 3 colors on any diagram that you get from the original diagram by pushing it around topologically. You never lose a color, you always have 3 colors. There are infinitely many of these diagrams, infinitely many of these categories, if you like. You're moving from one category to another. I think I need a formal definition of what it means to move from one category to another in this sense, but we could make one. And then that proves that the truffle knot is knotted. You see, if I really do convince myself that I always have 3 colors, then I've proved that it's knotted, because the unknot could only be colored with 1 color. So that's the simplest proof I know that the truffle knot is knotted, setting that kind of categorical way for fun. So that's the summary of what I just said. The persistence of the coloring proves the knottedness of the truffle knot. Now let's go to something more physical. Here's the title of a paper by Irvine and Kleckner. Kleckner is Irvine's graduate student, and they worked together and produced knotted vortices in water for the first time. No one has ever seen knotted. I mean, Kelvin theorized about it. People like Moffat and many other people studied this, how vortices would be, knotted vortices would behave in fluids. But until a couple of years ago, no one had ever seen in nature or in the lab a knotted vortex. It was often a question that people would ask, could you blow a knotted smoke ring? Which is a similar question. But nobody knows how to blow a knotted smoke ring. Somehow the dolphins know how to blow rings, but they don't. We've never seen a dolphin blow a knotted ring. So how did they do this? Well, in the upper part of the slide, you see how to produce an ordinary ring vortex. You could have a wall with a hole in it, and you push fluid through the wall, and it will vortex along the edge of the hole, and a vortex ring will emanate. This is how you blow a smoke ring. You have smoke in your mouth, you form a hole with your mouth, and you push and puff, and out comes the ring. So an alternate way of doing that is to form a little ring like this instead of a wall, where it's narrower at one end than the other, and pull it back through the liquid. And that's the same as pushing the liquid through, and the vortex ring will form and go forward if you pull the ring back. So their nice idea was, why don't we form a knotted framework to pull back through the water? And there's a picture of the knotted framework there. It's narrow in one direction than it is in the other, wider here. Pull it back, and it produces the vortex. They were able to do this flexibly by using 3D printing to make these plastic gadgets, which they would pull back through the water.
Does that mean the vortex has to heal?
So here's an unknotted vortex being produced by that method.
Does it mean the vortex has to heal as you pull that?
Sorry?
Does the vortex have to heal itself as you pull the thing away from it? Because one part's going to pass through the vortex.
Are you worrying about the other edge?
Yeah, you've got edges behind one another, haven't you not?
Yeah, it's true, but one is narrower than the other, and I'm sure they had to do a lot of tinkering to get it to work and not interfere with itself, yeah. That's where the 3D printing comes in, because you can very easily vary something, make another one, get it all to work eventually. Here's the
Yeah, I see
knotted
what you mean,
vortex.
Tony. It would kind of like superimpose, wouldn't it?
And you see
Slide
that
through itself,
this
yeah.
little film, the camera is showing you the three-dimensionality of the knot by moving around. You see it really is a trefoil knot. And of course, these break up fairly soon, which is another interesting aspect of them. You have a vortex in water like that, and it will tend to recombine with itself like this. It will come near itself and then break apart and come out like this, and you'll see more than one ring, and all the knottedness will go away under those circumstances. In order to do that, the vortexing has to be in opposite directions, so like this, in order for the recombination to occur. So if you want to think about it symbolically, there's an arrow along the line and another arrow like this, and if the vortexing is going like this, I'll put an arrow along the line.
They're on the side there, yeah, they're
Right.
the proper ones.
Thank you.
That's better, yeah.
This is a vortex line. This is the direction of vortexing around the line. So I'll take a right-hand rule and put a direction on the line accordingly. And then this kind of process of recombination can occur when these are going in opposite, these are going this way, then it can break apart, and then it will go and turn into this, like that. So that's the recombination. You can think of that, again, as some operation on morphisms from one category to another, if you wanted to. But what's interesting is that this means that there's a process in time that occurs with regard to these. For example, I didn't put this in the slideshow, that's why I'm bothering you with it this way. Consider that you had a trefoil knot like this, and it was a trefoil vortex like the one we have there, and it's going to break up. Now, in order for it to break up, you have to see things going in opposite directions to one another, and then it could break up. So as you see, it could break up between these two if these two manage to somehow come close to one another, right? Then it could break up. And what happens? Oh no, those are going in the same direction. I'm sorry. I wanted things that are going in the opposite direction. So that's a good point. You see, these can't combine because they're going in the same direction. These two arrows if you brought them parallel to one another, I'll draw it a little larger.
Yeah, no, I think so, yeah.
See, those are going in the wrong direction to combine.
Yeah.
Now, if it did combine that way, it would have turned into an unknot immediately. But that's not what happens. So now these two could combine right in here. So let's draw that. I'll just draw it larger. So it could combine along there, could reconnect there, these two. And then what would it look like after it reconnected? It would look like this. Sorry. Not drawing it too well today.
Can't see.
Yeah. If you step back, Lou, then
I'm going to draw this again.
Okay.
Yeah, if you go to one side when you've drawn it, then Roger can
Just
do the video.
I can get you a decent drawing on it.
Okay.
We want the process too.
Just getting it back.
There we go. And then where were the arrows here? This one and this one. Okay. So that's what happened to our truffle vortex after it recombined. It returned into a link. You see, and
So they are interlaced.
the link like that.
Yes.
So it's still knotted up. It's got linking in it, and it couldn't do anything better than that because of the directionality. So it needs more than one step in order to get completely undone. So if you have a knotted vortex and you think of how many steps does it need to take in order to get completely undone, it's an interesting topological problem. And this is a problem.
Yes, sorry, great.
Yeah, sorry, I was standing in front.
Rogers,
Yeah, so this is a problem of how knots might change in time. And you can even think about it geometrically in terms of four-dimensional space. Because this kind of recombination, each one of them can be thought of as moving through a saddle surface like this. You see? So if we started with this and we ended up with this, that's an example of happening temporally to go from one to the other. So then you can think of a knot moving through space-time, producing a surface. And then the question is, what's the least genus of the surface that you can produce that will get it over to an unknot? And this is a real problem about the way physical knots behave. And the truffle knot is obstructed from being able to do it without going through some genus. It has to go through a saddle and then go through another saddle. It ends up producing a bit of torus in between because of that link that's in there. And so this is an interesting problem. I'm thinking about it. That's why I kind of got off and started talking about it. So it's interesting to me that once you realize that something could be real, then your attention goes to it in a different way than if it was abstract. I could have thought about that same problem abstractly. In fact, I have, but then it makes a difference that it actually can happen in some system.
True.
You might want to see that film again. That's the first one. That's an easy one to look at. Let's look at the second one. Did you see the template at the bottom? I can't hold the slide in the picture very. Maybe there's a way. No, I should have taken a screenshot of the template that's sitting at the bottom. But with your attention on it, why not look again? Just a second. Back up. Now, quickly. Yeah, see? Okay. So that's one phenomenon wanted to mention. Now here is a little summary of some things about knots and links that are worth mentioning. The diagrams, we've already mentioned that there are diagrams, and what are these diagrams? They're graphs in the plane with four edges coming into a vertex with a little cut to indicate over and under, so that the line that's not cut is nearer to you than the line that's cut if you think of it being projected down into the plane. Then next to it are things labeled 1, 2, and 3, and those are each topological moves, like the ones I was doing on the trefoil knot a little while ago. And those topological moves turn out to generate everything that you need. That's a theorem of Reidemeister from the 1920s. So if you make diagrams of knots like this from their actual embeddings in three-dimensional space, and then think about connecting the diagrams to one another by moves of this kind, then that captures everything that can happen in three-dimensional space topologically. Which just goes to show that it's still complicated, but what happens topologically is a lot simpler than what happens purely geometrically. You can just use these simple graphical moves. The moves are to remove a one-sided region by pulling a curl, to remove a two-sided region consisting of going under and coming back, or to change a three-sided region into a different three-sided region by sliding a bit of rope underneath two other crossing bits of rope. The guy on the right is a picture of DNA, but I'll come to it in the next slide. I have a better shot of it there. Then the other things here are really quite significant, and you might not have thought of this, and knot theorists didn't think of this until a very good algebraist named Emil Martin had this idea in the 1930s. His idea was that you could put an algebra structure on knots by thinking of them as braids. So we all know how braids work. That is, you have strands and you weave them through one another like this. And if you have multiple strands, then you can have braids with many strands. And the idea of a braid mathematically, or here's another example of a braided leather belt, and we have three strands in the braid. And you have a set of points at the top of the braid, you have a set of points at the bottom of the braid, and then you have this weaving that goes on where the individual strands are not knotted at all, they just continue on down, but they weave through the other strands. In the case of the velvet braided belt, it's possible that the belt strands can have twists in them, but that's an extra structure. The notion of an abstract braid is just strands. And you see that if you have a braid, you could take, if you had a braid, suppose it's just this upper part, just to this point, right? There's a nice little braid, the upper part. And here's another braid, the lower part. But this whole braid is a composite of this upper braid and the lower braid, where the composition has been made by taking the lower points of the upper braid and attaching them to the upper points of the lower braid and forming a product. So that means that the braids form an algebra structure. So here's spatial forms, topological spaces, embedded spaces, which themselves form an algebraic structure. You can take two braids, you can multiply them, and they have inverses as well, because you see, if I were to, this is the simplest example here, I have this little bit of braid here, left to right, and this other one, right to left, two-strand braiding. But if I multiply them, then I get over and over, and it pulls apart, and it's the identity. I had two extra strands over here, so it's the identity on four strands. So every braid has an inverse in exactly that way. You just have the braid coming down, and then you look up at the braid and start putting untwists, opposite twists to every twist that there was in the braid in the opposite order going back down, and then it all will undo itself. So that means that for every one of the elements in this algebra structure, there's an inverse, and topologically, associativity works. So you have inverses, you have associativity, you have the possibility of multiplying any two, you have a group. So braids form a group. And this group structure is a generalization of the permutation group. Because you see, if you had any braid, take this guy here, on four strands, then strand number 1 goes to strand number 3, strand number 2 goes to strand number 2, strand number 3 goes to strand number 1, and strand number 4 goes to strand number 4. That constitutes a permutation of the numbers 1, 2, 3, 4. So if you just ignore the weaving in the braid, you get a permutation. And so the braid group is a generalization of the permutation group. Or to put it another way, there is a homomorphism from the braid group to the permutation group, which is to forget the topological stuff and just look at it as a braid group. And just look at it as a permutation. So that means that there is this interrelationship between the topology, the weaving topology, and very fundamental aspects of group theory. And the braid group turns out to be a very good way to try to study knots and links, but it's also been used to study lots of other things because it's a very natural generalization of the permutation group, and the permutation group is ubiquitous. So if you're thinking in terms of the permutation group, what have you released? In the permutation group, every time you have a transposition, I goes to J, J goes to I, it has order 2 in the permutation group, right? Because if you do it twice, it goes away. But in the braid group, if you have the equivalent of a transposition, which is a twist, here's a twist, and now I've done it twice, and I get a bigger twist. I've done it 3 times, and I get an even bigger twist. So what you released was that the square of a transposition is equal to the identity, no longer given. And so that's how you can think of what the braid group is. You start with the permutations, but then you release that the transpositions should have order 2 or any finite order. You just release it. You don't have it anymore. But you still have everything else that the permutations did. And then you're looking at the braid group. So the fact that you can think of the braid group as part of a more general, think of the braid group as a kind of generalization of the permutation group in that way, means that it ends up occurring in lots of algebraic situations as well. So there's the braiding. And then there's a wonderful theorem due to J.W. Alexander, which says that any knot, here's the figure 8 knot, for example, can be regarded as the closure of some braid. So in this case, here's this braid, sigma 1, or S1, S2 inverse, S1, S2 inverse. And closure means I take a strand at the top and I connect it down to the bottom. So I've done down corresponding bottom 1 to 1, 2 to 2, 3 to 3, and connect it up like that. And that, if you play with it a little bit, gives you the truffle knot, gives you the figure 8 knot. It's simpler to make a truffle knot by closure or the simple link we were looking at before. I wanted to digress for a moment and tell you how Alexander proved his theorem. So suppose that we were to take something really, I'll do it with something very simple. Here's a truffle knot, and it isn't a braid in this form, and I form a closed loop. All right. Now this doesn't look like a braid, it looks like a little knot on a rope, right? But what do you want for it to be a braid? What you want is that there should be an axis. Think of putting an axis right through the middle of that guy. And it will always circulate in the same direction around that axis. That's what you want when you want to turn it into a braid. That's a closed braid. Then you can cut it open and open it up and turn it into an ordinary algebra braid. But what you want is that the knot should be kind of vortexing, going always around the same axis direction, like that. So what did Alexander do? He said, well, choose some axis direction that you like. You have to ignore this knot that I made in my rope, because that's not the knot. That's just, I spliced it. And here's the knot. And Alexander says, walk along, keeping track of that axis. And when you get to a place where it doesn't seem to be any more going around the axis, why, take that bit of knot and throw it over the axis, making it, doing the job a little better of going around that axis. Good. Still not quite there, right? I'm not quite there. Now it's going around a bit more, but this part goes back on me, right? Not good. I have to get that to go around the axis. Let me see. didn't expect myself to be getting into a difficulty. Let me see. So, I'm just going to do this by trying again. You get the idea of throwing over the axis, but let's do a better job of throwing something over the axis. I'm going to throw this one over the axis, and now you see that I have, in fact, well, I should have. Oh. Great. Doing great.
Demonstration effect.
I'm going to throw this one over the axis. Yeah. And now it's a braid around that axis.
So now you can keep going around
so
in the same direction.
So the idea of this proof is that you find strands which are not correct with respect to the axis, you toss them over the axis, and now they're correct. And you keep on doing this. Now, if you're careful about it, and there's actually a rule if you're looking carefully, it's so hard for a lecturer who's trying to talk and do the rule at the same time, that you can systematically do it by just walking along, and every time it goes wrong, you throw it over the axis, and by the time you get back to where you started, it's turned into a braid that goes around the axis. So, with that idea in mind, you could discover the details of the proof yourself by tying it on in a rope like I did, a more complicated one, and then try to do this axial throw until you turn the whole thing into a braid, closed braid. So that's a fundamental theorem in the theory of knots. That
characteristic order then, is it on that?
pardon me?
Number of revolutions.
Oh, well, how many strands will you get?
Yeah.
Is that what you're
It's
asking?
characteristic order of the thing, is it something?
You might end up getting many strands when you should have gotten fewer.
Oh, you've repeated.
Because, you see, suppose I have suppose I have this one, well, I could always make it more complicated. I could. You see, I could put a little twist in it like this, and then that twist makes it not a braid anymore, but I'll put it around the axis. And then I get a braid with more strands. I can keep on doing this.
But there's a minimum number then.
So you'd like the minimum number, of course. But it's one thing to say that you can always convert something into something else, and then another thing to ask, how do you get the minimum something else that's possible? So that means there has to be something to think about there. There's a lot to think about. But nevertheless, you can study knots by studying braids, and that's the content of this slide. And I wanted to tell you about the braids, because it's also another aspect of category. You see, a braid, and you can compose them, well, a braid has a direction, and it's sort of like an arrow. It's sort of like a big, complicated arrow. So why not think of it as an arrow? Then it's an arrow in a category. What are the objects? Little rows of points. The objects are very simple. Just a little row of points. And the arrow is the braid, which goes from one little row of points to the other. So this is an example where, a very good example of how in categories, the arrows are not necessarily maps of sets in any sense. They are just structures, and you're looking at relations between one structure and another. The objects have no internal structure, they're just little rows of points. And the braids can be thought of as a category.
But hang about, but it's what happens in between the points. I mean, because lots of things
so
happen in the braid.
the arrow actually has a lot of structure.
Okay. Not sure if I got all this.
Arrow isn't necessarily just an abstract arrow. That's why you don't say arrow all the time, say morphism. Right.
But so you start with a set of points here, and then you've got various points going down in a braid, haven't you? And then you get to some...
Right, the arrow goes from, you have the language, it goes from an object to an object. Well, the object is just a little row of points.
Right.
I might call it 3, for the integer 3 if I wanted to give it a name.
Yeah. And so what are you saying about the other points on the way? Or that's...
What am I saying about?
About the other points on the way? Because
I'm not saying anything about the points along the way unless I wanted to.
I'm just wondering how that... Because
I mean, it's just like the pace thing, right? If you have a braid, then there's this fixture at the bottom, and little row of points, and a fixture at the top, little row of points. But when I multiply two braids, the fixture at the top of this braid and the fixture at the bottom of this one, they get released. They get, the braids are welded and they get released, and then all this can move freely topologically, right?
Yeah.
But the fixture at the top of the upper braid and the fixture at the bottom of the lower braid, they stay fixed. Those fixtures are the object.
Yeah, okay. I'm just sort of thinking that you could lose structure, that's all I'm thinking. If you're just defining it as these points and these points, you could be losing structure of a braid. You know what I mean? It could be like a much more knotted braid and you'd still end up at the same end point.
Well, sure, I mean, I need to have a context in which braiding can happen, right?
Yeah,
And in that context, the braid is seen as a morphism.
okay. I think I'm kind of in the area.
I mean,
Yeah.
it's always that way. I mean, categories have to do with relations between something and something else.
Yeah.
Morphism
I mean, I'm
has to do with
still,
some relationship.
I'm still struggling with categories.
I'll come back to that, but I see we're going to do not everything, for sure. This is just for fun. You could try to see whether this was knotted or not. But I'm not giving you enough time to look at it. So, the DNA is a good example of applied knot diagrams. And how did that happen? Well, this is an electron micrograph. It's an electron micrograph of knotted DNA, and it was after they made this, in the context of their experiments, that they could say quite confidently that DNA can be knotted. What Spengler, Stasiak, and Casarelli did back in 1985 is they had very good techniques for coating the DNA with protein to make it thick. And then they take the electron micrograph, and then you can see that the DNA is going over, weaving over and under in the flattened pictures of the DNA. And so they could see the weaving. And they're confident enough in their procedures to believe that this actually is a picture of the weaving of this microscopic entity. So, you can't come to their belief without knowing all the details of the experiment, but it's easy for us to come to a secondary belief by looking at the picture. And it is, and in the end, it's a knot diagram, and you might even wonder, where is it in the classification of knots? And if you were to look closely at it, you would see that it happens to be this one. These are the first few knots labeled the way Rademacher labeled them in his tables. So it's the second six crossing knot. But that can be done. And there is an active field in biology of using knottedness of DNA for various things. In particular, well, I have the slide, so I'll mention it. This is that same idea that was happening with the vortices, but a different kind of recombination. Instead of reconnection, the way I showed you, this is DNA recombination, where two edges come near one another and are replaced by, they get cut apart by enzymes and are cross reconnection, like that. The question that people had about this was, which way does it crossover reconnect? Does it crossover reconnect left to right or right to left? Or maybe something more complicated. Well, you can do a thought experiment. You can say, I have a non-knotted DNA, like on that picture, and then you would assume that it crossover reconnected from the top left to the bottom right. Yeah? And it does that way every time, and you do a successive process of them. Do one, then do another, then do another, do another, and you get a sequence of knots and links that come out. The first time you did it, you got a little Hopf link like that, then you got a figure-8 knot, then you got somebody else, then you got somebody else. And so what they did was, they did a controlled recombination, so they knew what was happening in that geometry. And then they looked at the electron micrographs, and they saw those knots coming out. not other knots, but these knots for the specific DNA that they were using. And then that provides extremely good evidence that, in fact, the recombination was with this handedness. Because if you did the same thought experiment, you might be interested in trying it with the opposite handedness, you get a different sequence altogether of topological things. So the local and the global in topology are now operating to give you scientific evidence about things in that way. And that's the kind of research that's been going on since that time. And I wanted to mention that. It's not physics yet. Here's another morphic example. Here's something that's more general than a braid, called a tangle. And in a tangle, it's just like a braid. You've got points at the bottom, points at the top, some strands in between, but that could be knotted, and there might be some individual strands that never did anything but circulate. That's a tangle. And you see a tangle can start at 3 and end up at 5, right? It doesn't have to go 3 to 3, and now it's really a category. I mean, you have lots of objects. You have 2, you have 3, 5, 7, 117, all those different integers for objects, 0 included, because it might never go from anywhere to go from anywhere. So that's a morphism from 0 to 0. And so there's tangle category, and one uses that as well. So these categories that I've been mentioning are ones that people use all the time. The notion that a knot itself is a higher category, that seems to be something that I may be the only person who's worrying about that at the moment. Here's another example of category and decomposition. You see the horizontal pieces are small individual morphisms from 0 to 2, from 2 to 4, from 4 to 4 with some kind of funny thing, and so on. And it starts in 0 and it ends in 0 and it goes through a dance in between. And you can also interpret this in other ways. You could think of this as vacuum at the bottom, two particles get created, then 2 particles get created, then some particle interaction occurs, then some particle interaction occurs, then some particle interaction occurs, then 2 particles get annihilated, and then 2 particles get annihilated, and you have a vacuum process. So you can use these in various ways. Now we're verging on about 7 minutes left or something like that. So I'm going to skip forward.
You've got 12.
I'm going to sort of...
We've got 12 minutes.
You've got 12.
12?
Well, that includes questions.
The big 12. I'll think 12. This slide is a philosophical point that the knot, as topological knot, is information independent of the substrate that carries it. So,
This is Stephen, who's going to talk tomorrow.
yeah.
Who hasn't been here for a long
Stephen.
time, but some people might remember back in Cambridge days. Good show.
A tie a knot in this rope, and the knot itself needs the rope for you to see it. I can't have a knot without some kind of substrate. I make up mathematical, imaginary substrates for the knot to live on, but like an abstract curve. But there it is, and once you have a substrate, you can have a knot. But the knot isn't the substrate, it's something that the substrate carries. Like a signal is carried by, like information is carried by a radio signal. And this same knot, trefoil knot, could be made out of many other things. It could be made out of a blue rope instead of the red rope. It could slide along and disappear off the red rope and turn into the blue rope, and so on. So it's information that's independent of the substrate. On the other hand, if you try to take into account the physicality of the knot, as everybody did for thousands of years, well, then you get other properties, and let's not forget what they are, because they lead to all sorts of questions that people don't really know the answers to. For example, this is one you understand. You tie a square knot in two bits of rope to splice them, and this produces a tremendously good splice. That's a physical fact. Why does it work? Well, each loop in the square knot constricts the base of the loop of the other. Each loop constricts the base of the other loop. So and when you put force on here, each one of them is tightening up the other one, and it gets very strong, as long as there's some friction. You just need a small amount of friction, and then it's good. If you make the wrong sort of construction, like you think you're making a square knot, but you make the wrong one, you make this one, which is sometimes called the granny, but I once said granny in many years ago, and the feminists in the audience got very upset. So I'll just call it the wrong square knot. But you see, this one doesn't have that kind of grab and constrict. And the frictional forces will let it slide. And so probably it will come apart, or at least begin to come apart if I pull it quickly. And if you were on a mountain, that would be bad. And so there are a lot of interrelationships between the substrate and that knotted information that's independent of the substrate. Another example that everybody knows, but you might look at, is the bowline, well-known knot, where this is another one of those cases where a loop is formed and grabs, and then you have this larger loop which might be around your waist, and this works very well. When there's a force, it grabs perfectly, very, very good. But on the other hand, when there's no force here, it's very easy to just flip it apart and take it off. So there's all sorts of things about the way the forces work that really bear more analysis than we know how to give them. There's an open field of study there. And one of the most easily stated problems that's sort of in that field, doesn't even have to do with forces, is what's the least amount of rope you need to make a knot? So I have a rope of a given diameter, or an abstract mathematical material of flexible, that's flexible but has constant diameter. I could make an abstract mathematical material like that. And then I can ask, what's the least amount of rope, that material, that I can use to make a knot? Well, it turns out it's about 12 diameters for a trefoil knot, but that's experimental. Nobody knows the exact ratio. So you have the ratio of the length of the knot to its diameter, which is like pi, the ratio of the circumference of the circle to its diameter, but we don't know the number. We don't even know an exact, say, power series for it. No exact expression, just computer evidence about those things.
Because when I first met you, that was a conference in Cambridge when they were talking about that. And that's like a while ago.
Oh, yeah, it hasn't progressed that much.
Yeah, no, that's very, because it is really interesting.
But every knot has a constant associated with it. We call it rope length. It's the length of the knot divided by the diameter of the rope. So it's a scale-free constant. It's a topological invariant of the knot. We don't know what it is. We have no way to calculate it other than use computer programs to approximate it. So that's an example of how, well, if you want to bring in the substrate, then the interrelationship between that abstraction and the substrate is difficult. It's a mind-body problem. Now, at this point, I am going to skip something, so you'll just pardon me. I'm going to just slip through the slideshow. You may have heard me talk about some of these anyway. This will go too fast for you to see. I'm sorry. I can't resist this one, though. The Bromian rings is a well-known example of three-linked rings, such that if you remove one of them, the other two fall apart. Why are they linked? Well, if you played with my coloring game, we could prove it by using coloring in a certain way. But the intuitive idea is hard to bring into the mathematics. The intuitive idea is very clear to everyone, but it's hard to bring into the mathematics. You see the intuitive idea. Red is surrounding blue, blue is surrounding green, green is surrounding red. It's a scissors, paper, stone situation. It's clear to all of us that that is integrally related to why they're linked. But any proof that I write down tends to obscure that in some funny way. Not completely. Some proofs that use a lot of machinery actually sort of look like that. I should talk about quantum mechanics, but we all know the postulates of quantum mechanics. And I was going to talk about entangled states in relation to entanglement, but we'll skip that too. Knots may be related to polyhedra, like you might weave a knot on a surface. I can't resist saying a word about this one because it's related to something that you can do that's a good experiment. If you take a strip like this belt and you tie it in the truffle knot, and then you try to make it flat by removing as much twist as you can from it so it can flatten out, and pull it up, you will find that you get a very nice pentagon. All right? So the dimensions of that pentagon are also a scale, up to scale 3 again. Take the ratio of the length of the pentagon to its side or something like that. Or take the length of the amount of rope that I used to make it to the edge. And you'll find it's related to the golden ratio. I want the total amount of belt to the edge of the belt, right? Just like I said for the other. But here we can get the exact number, at least conjecturally, because it pulls up into a perfect pentagon. And that's a relationship between knots and polyhedra. That's fundamental, or elementary geometry. So this is a very nice experiment to do, just to take a piece of paper or a belt and see it happen. Try it for more complicated knots, and you'll get more complicated kinds of things there. But again, there's an unsolved problem. I don't know how to prove that this perfect pentagon is indeed the smallest amount of belt I can use to make the truffle knot. I don't know how. But maybe that's easier than the other problem. So knots and polyhedra, and then there are more recondite possible relationships between knots and polyhedra. Richard mentioned that the universe might be I forgot the way he was saying it.
ADS5 dodecahedral.
How did you call it?
Anti-de Sitter 5-dimensional space dodecahedral.
You called I would say the re-entering dodecahedral space, and you said something else about going around and coming back.
Oh yeah, well it's called by Lumiere, it's a wraparound universe.
The wraparound, wraparound's a good term, the wraparound dodecahedral space. So the universe might have the shape of a dodecahedron, but the opposite faces of the dodecahedron, let me take this picture. The opposite faces, like QPRST below and QPRST above. When you travel in the universe from the above place to the below place, you end up back in the above place. It's closed up. It's closed up for every pair of faces like that. So the dodecahedron is an unfolded or unwrapped model of the three-dimensional space that we're thinking about. You can't put that three-dimensional space that I'm thinking about into 3 space. It would be like you took a cube and you said, well, it's like a 3D video game. The right-hand side of the cube goes, anything that goes through the right-hand side will reappear on the left-hand side, top to bottom, front to back. Only this is the same thing with pentagonal faces. So the universe as a whole, as a 3D geometrical, might be this one. Some people think it might be this one. So there's a colorful notion. For some reasons, it might be this one. Let's suppose it is. Then the universe would be intimately related to the truffle knot. It's not obvious, is it?
Well, I'm sure, I believe deeply that the universe is related to the truffle knot, but I don't know quite why.
So, I mean, this
the
is
link
like,
between
how many impossible things should I ask you to believe before breakfast? But suppose that the universe was this space, this dodecahedral wraparound, right?
Yeah.
Well, the dodecahedral wraparound has some very nice symmetries. You're looking at one of them. Imagine an axis that goes through the front face, through the middle of the front face, right down through the middle of the back face, right? Then you can turn the whole universe around that axis by 1/5, and everything goes back to itself. PT will turn into TS, and so on, and the whole universe will be nice and symmetric around the axis of symmetry.
Can you go back to the from the slide? No, the one with the pentagon. Before. Yes.
Oh,
So there, if you take the star pattern inscribed in the pentagon, it's recursive.
yes, that's true.
And then that may explain why you return to yourself, because it's the sequence.
Are you looking for an explanation of why the universe might be, but I'm not trying to explain that.
No,
But it could be, it could have to do with recursiveness of some sort.
So,
Yeah, but notice that you don't ask in the light of Copernicus and Galileo and other people, you don't ask why the sun goes around, the earth goes around the sun. And you don't ask why is it that when I travel all the way around the earth, I end up coming back to where I started. It's part of the geometry of the earth that you know. So it could be part of the universe that you know that it has this kind of, comes back on itself. But of course you can ask, why would that be true? And I wasn't asking that.
I know.
Would that be
but
true? With the flat universe, though, that we now have, the Euclidean.
It might be fractal and there might be a recursive
So
reason.
here you have a recursion, and then it becomes a self-reference.
But I think we're verging on out of time. Let me wrap up for a moment.
Yeah, can you go back to the image of the dodecahedron and back to the labelled one? That's right.
But what I wanted to tell you about
Okay,
was how this dodecahedral wraparound universe is related to the trephone. Okay?
please.
So a dodecahedron has many axes of symmetry. I'm going to concentrate on one of them through opposite pentagonal faces. Okay? Then you can turn by 1/5. All right? Now, it turns out that if you were to take the dodecahedral wraparound universe and identify a point with the 1/5 turn point, you would collapse the whole universe, right? Into, like, it would be like taking a pie and collapsing it to one of its slices, all right? You could imagine doing this. You get another space. It turns out that the space you would then get would be a three-dimensional sphere, an ordinary three-dimensional sphere, which is also a wraparound. The three-dimensional sphere is a closed thing. And the axis, remember the upper point on the axis and the lower point are identified. It's a circle. It was a circle in the original universe, that circle. That circle ends up turning into the truffle knot downstairs in the collapsed space. So that the wraparound dodecahedral universe collapses or maps down to 5 times to 1 the three-dimensional sphere with a truffle knot in it. Or to put it another way, you can start with the three-dimensional sphere with a truffle knot in it and form a covering space branched along the truffle knot. A 5-fold mapping to 1, except along the truffle knot where it's 1 to 1, and it goes around cyclically like that. And that would form the real universe. The real universe would be this 5-fold expansion of our usual picture of the geometry of the truffle knot in 3 space. It takes some work to see that, and I'm not going to try to prove it to you because we're out of time, but it's related to thinking about certain algebraic varieties like the one that's at the bottom of this slide. So we could end this slideshow long before its intended end with this slide.
What's the relation of the truffle to the three torus?
Relation of the truffle to the
Three torus. Three torus. Two torus.
of the 3 torus. You have the 3-dimensional torus. Well, the 3-dimensional torus, but he says the 3-dimensional torus. Let me explain what I think he means. I think he means something with 3 coordinates, like the torus has 2 that are circles. All right? Torus has 2 circular coordinates. 3-dimensional torus has 3 circular coordinates. Cartesian product of a circle with a circle with a circle. That's the same as taking a cube, excuse me, a cube, and identifying top to bottom, right to left, front to back. And that turns out to be related to the Borromean rings in a very nice way, for which there is a video, which happens to be on my computer, and I won't show it now, but if somebody wants to see it, I can show it to you. But it's more closely related to the Borromean rings than it is to the Teflon.
But you can't, they're not homeomorphic or old, they're not, so I mean, because the Calabio is a test.
It's not Calabiana.
It would be nice if the Calabio manifold, because then you tie right into the dodecahedron.
It would be nice, yeah.
But so you're saying that.
Well, I don't know what those relationships might be. They're easy. So there are a host of very interesting interrelationships between knots and physics. I was going to talk about some elementary particle relationships and so on, and maybe I will slide some of that into the next slideshow on Thursday a little bit. But I hope you see there's a rich subject here for speculation and also for investigation.
I'll just mention one thing it ties together what Lou's doing and your stuff, Peter, because I did this fantastic course of invertible forms, and apparently these started with this guy, I can't remember, so it was in the 19th century, in the 20th century, early 20th century, Schatz, because it's the Schatz cube, so it's Paul Schatz. And he started with this astronomical question, which was to do with the dodecahedron as the universe. Right? And so for some reason, I don't know quite why he was doing this, but he kind of did this path, closed curve, to go through all the pentagonal faces, which kind of went round like this. And for some reason, again, I know, there was something to do with he had this thing about feeling form. And somehow this.
Can you find that reference?
Well, let me just tell you, because there's this thing about Sitter-Wegeln unit, because he decided for some reason, because when you do this close, like the minimal closed curve goes through some pentagons with 2 crossings and with some with 4 crossings, and this felt kind of like a bit imbalanced to him, and so for some reason he decided that he needed to cut the dodecahedron, and when he did, there was something it could kind of open in a way, or he took out, the first time he took out a bit, it went into, you know what invertible forms are, don't you? That they're kind of like, so they're 3D shapes that you can keep twisting round and round and round. I brought some with me actually, but I haven't got the dodecahedron. That would have been too complicated for us to make. But the thing was that the first one he did only had a little bit of movement, wasn't totally invertible. He then went on to make the invertibles. When I saw that, I said, nobody there knew what I was talking about. I said, maybe that's like Sitter-Wegeln. And so I just, yes, there must be, I haven't looked on the web, there must be somebody must have done images on the web. But I'll bring in, because I was wondering whether to bring them in, I will bring in the Schatz cube, because that's where he got to, and that's led to the alloy, which
there are some nice thematic relationships here with things that other people are talking about. For example, Peter likes to talk about space and counter space. And I think that in the topology, that's worth thinking of analogically with the knot and the what's not the knot.
Yeah.
You see, like here's this knot, and what's not the knot is all the rest of that complicated 3-dimensional space that isn't the tube that you see.
Yeah.
And of course we studied that. But that's sort of the counter space or the anti-space to the knot.
Yeah,
right.
yeah.
Lou, are these trefoils in the middle of the Borromean ring?
Huh?
Are these trefoils in the middle of the Borromean ring?
Oh, yeah, you
These are
must
just
stop us,
rings, right?
I googled
The formal session is over.
I'll show you one last film. Here's the contraction of the truffle knot to its least form. And if you watch that, you see why, you get an intuition about why this problem is difficult. See that little last, what was going on there? Now you see it in the experiment, but what differential geometrically is going on there? That little last pull-in.
Yeah. It's the Ouroboros. That's why snakes need smooth skins.
It's got to have to do with 137.
Yes.
It's definitely.
To deal with that.
Google image